our lesson today is looking at multiplying vectors by scalars. So remember, a vector is a particular quantity with a direction. A scalar is just a number. So what we're going to try and do is multiply vectors by numbers. So remember now we've taken care of a few different computations, I guess, calculations with vectors. We've managed to do vector addition already. And so now we've done vector subtraction. So now we want to do scalar multiplication. So I'm just going to take a little step through it here. I guess we're going to start with vector A, and we're going to say that vector A has a magnitude of 5 centimeters, so I've got it drawn here. What we want to draw is a new vector called vector U, which will be vector A plus another vector A. So what I'm going to do is I'm going to just grab another vector A here. And remember, they have to be aligned head to tail. So we'll put it right there. And that's created vector U. Vector U was supposed to be A plus A. So I could draw it this way maybe for us. That whole thing would be called vector U. So this is absolutely correct. I mean, we've managed to do this just by adding vectors together. But you can probably imagine if I was going to add a whole bunch of vector A's, this wouldn't be a great way to write it. So this is where our scalar multiplication comes in. We can simply write it this way, and I think it's probably what you would have expected. It's vector U equals 2 vector A's. Or we could have had some vector equals 5 vector A's, and we just would have had all those vectors added tail to tail. In a sense, then, all this has done is it stretched things. Right? It took vector A, and it doubled the length of it to create our new vector. So we're saying that the direction is the same, and the magnitude is now double what we originally had. So the magnitude of vector U is equal to the magnitude of vector A, but times 2. And the direction is the same. So that's the idea of how our scalar multiplication is going to work. This is sort of a few of the official rules. I don't think anything here will surprise you too much, but this is more of the official stuff that we need to make sure that we have down. It says let vector V be any vector and K be any scalar. And just notice the notation. For vector V, I've got the arrow on top, whereas for the K there isn't. K is just a number. So if we have those, then K times vector V is going to create a new vector that's going to have this a magnitude that can be calculated as follows. It's calculated as the magnitude of V times K. And then the direction follows based on these next 3 bullets. So it says if K is greater than 0, then it's going to be in the same direction we just had. That was the example we just saw, right? Vector U was 2 vector A's, so it's going in the same direction. Well, if I changed that and made it -2 vector A's, it would have had the same magnitude, but then it's just pointing the opposite direction instead. And then the kind of silly case, but again, we have to make sure that we cover everything. K could be any number, right? So here we've got K is greater than 0, K is less than 0. If K actually was 0, then we're taking our vector and multiplying it by 0, which just creates the 0 vector. So not particularly exciting there. Little note for us, this helps occasionally, the idea that scalar multiplication is distributive. And I think I can show you a bit of a picture of how that will work. If I had vector U here, and then I had vector V, kind of like that. So U plus V would be here, okay? What I'm saying then is that if we were going to make things larger, I'll do that in red maybe. Here's vector U, but maybe doubled, for example. Okay, so I've multiplied vector U by something, and then I've multiplied vector V by that same number. So they're both a little bit bigger. Then the resultant is just K times that number, K times that vector. Okay, so we're just saying that the red vectors and the blue vector there are equivalent in the end, so we're allowed to distribute through. Now, I was just looking at what I'd written above. Back up here, we said kv is a vector with magnitude k times vector v, or sorry, k times the magnitude of vector v. We have to be a little bit careful there, and I wasn't specific about it before, because in this second bullet, I said that k could be less than 0. So if k is less than 0, that doesn't mean that our magnitude is less than 0. We can't have a negative magnitude. So I'm thinking maybe a better way to have written this statement would have been like this. So what I'm saying there is, I guess I'm using the same symbol to do two different things. Around the k, I'm using the absolute value notation. So remember, absolute value just made everything positive. And then around v, I've got the magnitude symbols. So either way, all we're saying is that no matter what magnitude we get, the answer should be positive. Okay, I don't think it'll be an issue, but it's something we should keep in mind. Okay, consider the rectangle ABCD shown with x, the midpoint of AB. I can put that on right now. There's x. And with y and z dividing AD into 3 equal parts. So I hope you can picture what I mean by that. Point x was the midpoint of AB. Y and z are points that are going to divide AD up into 3 equal segments. So we can't really call it a midpoint, but it's got that same sort of idea. I'm hoping those points are close. So there's y and there's z, and now all 3 of these lengths are equivalent. Well, I came close. Let vector p equal vector ax. So that's this guy right there. There's a vector p. And let vector q equal a to y. There's vector q. Okay. So we have vector p and vector q labeled in our diagram. Write the following vectors in terms of p and q. So what we want to do is I'm going to give you a vector. You can see there vector ab. And what I want you to do is rewrite ab in terms of just vector p's. So I need a vector ab is equal to, and I hope what you can see there is since x is the midpoint, one vector p gets me to there, and another vector p would get me all the way to b. So vector ab is vector p plus vector p again, which of course we want to write using scalar multiplication like that. So vector ab is equivalent to 2 vector p's. Vector dA. So starting at the bottom left, and we need to get all the way to the top left. So this time we're going to have to use vector q, but we're going in the opposite direction. So it's going to have to be a negative, and we need 3 of those distances in order to cover the distance. So we can write that as minus 3 vector q's. Again, 3 q's would take you from A down to D. I'm putting the minus in front because I want to go in the opposite direction. Okay, a little bit trickier because now we're going on an angle. Here's vector yb. So we're starting at y, and we want to get to b. So if we're starting at y, we need to move in either the direction of p or q or the opposite direction. So I think our best bet is probably to first go a negative vector q. That'll take us from y to a. And then 2 vector p's would take us from a over to b. So that'll work for that one. And same idea here. This one might even be a little bit easier, I suppose. We want to go from y to c. So we're starting at point y. Let's go all the way to the bottom. So to get from y to d, that would be 2 vector q's. And then to go from d over to c, that would be the same as going from A to B. So 2 vector P's. Do keep in mind we didn't have to write it in that order. We could have done this too. Okay, that would also be correct because addition of vectors we said was commutative, didn't matter the order. And what we saw on that last slide with the little note, it had talked about the distributive idea. So we could even write it like this if we'd wanted to. And I just wanted you to be aware that all 3 of those answers are equivalent. They're all the same, just different ways of writing it. Okay, before we go into the next slide, there's just one other thing that we need to see will help us a little bit. I'm going to sort of randomly pick some other point here. I'm going to put a point, I don't know, maybe about there. Nothing special about that point at all. Let's call it point K. So there's some point K, and I'm not giving any indication at all about how far down it is from along that line segment BC. What I'm wondering is it possible to make, we'll call this E, is it possible to write a vector AK in terms of P and Q? Is it even possible to do that? Because I haven't given you a location, but I'm wondering if it's still possible, if we were, I don't know, if we were able to measure or something. And the answer is yes. Part of it I think you can see where, first of all, we could just go from A to B. So we could use 2 vector P's to get somewhere over. And then if I want to go from B to K, Q, just 1 vector Q isn't enough, right? That doesn't get me far enough. 2 vector Q's would be too much, it would get me past there. So it's got to be some number in the middle. We don't know what it is, and honestly, I don't care. We don't need to know it. That wasn't the important part of what I'm trying to show you. All I want you to recognize is that there is some number that we could put there that would get you to K. Okay, there's some number that would be possible that would make that happen. And it's probably around 1.5. Okay? So what if I did this then? What if I put another point somewhere even more in the middle? If I put that around there and I call that point L, would it be possible to write vector AL in terms of P and Q? So we're trying to get that vector right there. And the answer is still yes, but it's also a case of we wouldn't know what the numbers are. So if we want to get from A to L, we would need some number of vector P's and then some number of vector Q's. So we could get there, we would just need some odd number. What's important there, those numbers, the values I've got for M and N, they don't have to be nice numbers like 2, 3, 4, negative 2, 3, 4, whatever. They could be any decimal I want. Okay, so those are any real numbers. So if it would be possible for me to come up with the right numbers there so that I could get to point L. That means that really I could have put point L anywhere. It doesn't have to be inside the box. I could move point L somewhere up there, right? I could move point L way down here somewhere. Wherever it is, it's always possible for me to come up with an answer. It's always possible to come up with numbers that'll move P and Q and eventually get us to point L. That's an idea called a linear combination. So first we need to define what collinear vectors are. It says 2 vectors are said to be collinear if they're in the same direction or if they're in opposite directions. It doesn't say anything about magnitude. So all we're talking about here is same direction or opposite direction. So for example, that vector and that vector, minus the fact that I haven't drawn them perfectly, would be collinear. Okay, they're going in the same direction. This one, still collinear. It's going in the opposite direction, but that's okay. They're still in the same, they're still called collinear. Remember, if I make, say I do this, now we'd actually call them opposite vectors. When I'm talking about collinear, I don't care about the magnitude. Okay, all we care about is the direction. What's important there is if I have, say, one or more vectors that are collinear, it doesn't allow us to move around much. Right, let me back up for a second. When we had our vector p and vector q here, if I had never given you vector q, we couldn't have done many of these questions, right? We'd only be able to use vector p. That'll allow us to move right as far as I want, or we could move left as far as we want, but we'd never have this ability to move up or down. If I only gave you vector q, we could only move down or we could only move up. It's the fact that we have both of them that's going to allow us to move on angles and diagonals like this. So if I had more than one vector that are in the same direction, it's the same problem. I can only go to the left or to the right or to the up or down, or in this case, I guess on an angle, but I would never be able to move outside of that line. So the second sentence there, it says a linear combination of two non-collinear vectors. So non-collinear vectors is now any two vectors that aren't in the same or opposite direction, right? This would work. Here's vector v, here's vector u. They're not in the same direction. If we have two vectors that aren't collinear, then they can be used to represent any other vector in two-dimensional space, or sometimes we just call it in two space. So if I use vector u and vector v, I could say put them together. Whoops, looks like I can't put them together. If I move vector u, right, that would create a new vector, a sum of this vector right here. What I'm saying is that if I took some multiple of vector v or some multiple of vector u, I could create any possible vector that I ever wanted. Okay, so if I really wanted to make this vector right here, it would be possible to use a few vector u's and a few vector v's to actually create that vector. And that's what we want to do on this final question. It says consider vectors a and b drawn on the Cartesian plane. So I've got them drawn there. Write each vector, which I'm about to show you, as a linear combination of a and b. So first thing, it's important there. I'm assuming this is the first time we put anything on a grid. I've got vector a and vector b both starting right at the origin, and my intent is that vector a is ending at exactly the point 2, 1, and vector b is ending at exactly the point 1 minus 3. So I'm being really specific about where they are. Okay. And it's kind of nice to have them on a grid because it makes it a little bit easier for us to picture exactly how things are working. So there's vector u. I hope you can see that. It's a little bit tricky to see in the green. What I want you to do is write vector u in terms of vector a and vector b. So is it possible to create vector u out of just a's and b's? And what I said a second ago is as long as a and b aren't collinear, and they certainly aren't, they're not the same direction or opposite directions, then whatever I pick here, it has to be possible. There needs to be a way to create vector u from vector v. And hopefully you can see it. All I have to do in this case is pick up vector v and move it to vector a. So now that they're aligned head to tail, it's going to create vector u. Remember here what vector b does is it went over 1 to the right and down 3. So from this point here, over 1 and down 3 will take me exactly where I need to go. So vector u is equal to vector a plus vector b. Okay. Let's try the next one. There's vector v. So can we write vector v in terms of a and b? And again, it's going to help to think about how these vectors move, right? Vector b has the ability to move 1 to the right and 3 down. Vector a has the ability to move 2 to the right and 1 up. But keep in mind, we can go in the opposite direction too. And that's going to help us on this one. So, I mean, at this point, there's not really a great method for doing this. It's kind of a visualization problem. The way I'm seeing it, I think I would start with vector b because it's at least close to vector v, and I need to move to the left and down. So if I was at the head of vector b, and then I wanted to go here, I think that's just a minus vector a, right? 2 to the left and 1 down works perfectly. So vector v would be, I could write it as maybe vector b minus vector a, or I could have written it this way too. It's also correct. Okay. So we've managed to do a couple, and there's vector u and vector v. We've managed to write them in terms of a and b. There's vector w. So can we make vector w out of a's and b's? This one's harder. Okay, so this one's quite a bit harder than the last one. Let's see if I can draw in. I can do it like this. Here's vector b. I'm not going to put an arrow on it just in case I want it to go another direction. But here's vector b, so I'm allowed to use that. And here's a vector a as well. So I'm allowed to use that. Okay, so I can sort of move these around and try and create new things. So maybe if I put vector b right onto a, we remember that created this one, that's no good. I could go up. Oops, not quite. Could do that. That's kind of close. And in fact, if I toss vector a on there, it's actually going to line up perfectly. That's a miserable way to draw it, though. I'm going to do it this way instead. Move that out of the way for a second. I'm going to do 2 vector a's. Okay, so I'm going to head that way. And then vector b after that. Okay, so to create this one, I needed, what did we say, 2 vector a's. And then I went in the opposite direction of vector b, so a minus vector b to make that one. Now, my guess is as you were looking at that, you weren't able to see that right away. Usually you can get it after a few minutes. You can kind of look at it and work your way through it. So it's possible. But it certainly becomes a more difficult problem than finding u and v. So then we're going to try x. So there's vector x. And I want to try and write that in terms of a's and b's. So we couldn't really fit it too well on the grid, but my hope again on vector x is that it's going to end at the point minus 8, 3. So 8 to the left and 3 up. What I want you to recognize now is that this should be quite a bit harder. If vector w was tricky, this one's going to be much harder. And if I picked a point way out there, it's going to be harder still. However, I'm saying that it's possible. Right? I said before that if vector a and vector b were not collinear, then there should be some linear combination, some multiple of a and some multiple of b, that if I put them together, I should be able to create any vector I want. So the question then becomes is how the heck are we going to find it? We know that we're going to, well, we're trying to create this, I suppose. We want to get vector x in terms of some number of vector a's and some number of vector b's. Right? That's our goal, is can we come up with what m and n have to be? We don't know what it is yet. But this time we're going to try and find it. So they could be anything. They could be any real number. We want to try and figure out exactly what they are. To do that, we need to consider what vector a is actually doing. Vector a is giving us 2 movements in a sense. It's going to go right 2, and it's also going to go up 1. That's what vector a can do. Vector b can go right 1 and it can go down 3. And we get both, right? If we use vector b, it's going right 1 and down 3. They both have to happen. If we use 2 vector b's, then we go right 2 and down 6. We could do in the opposite direction for vector b. We could go left 1 and up 3, but they have to go in pairs. Now think about what vector x needs. Vector x needs to go left 8, and it needs to go up 3. Right? That's our requirement. We have to somehow make that happen. So how are we gonna do that? Well, if we just start considering these possibilities in terms of those movements, we don't even really need to see this grid anymore. I'm gonna get rid of it if I can. I'm gonna slide it up here. Oh, here, I think I can get rid of them this way. There we go. Let's just give us some blank space. We want to get vector x by using a certain number of vector a's and a certain number of vector b's. I want to think of it in terms of left and right movements and up and down movements. So let's first do the right, left. Oops. I'm going to use a certain number of go to the right 2's. Right? Vector A, we're going to use m of them. So m times, I'm going to move to the right 2. And then n times, I'm going to move to the right once. Now that's not usually the way we would write it. We'd usually write that as 2m plus 1n, right? That's much more like we're used to seeing. But what we need out of that, the result, has to be a result of left 8. That's what we have to get in the end. So to show a left, we can just put a negative there. So remember what we're saying there is we're going m times 2 to the right, and we're going n times 1 to the right. We have to end up with minus 8 in the end. So certainly either m or n better be negative, because we're going to have to get a negative answer at the end. Same trick for the up and down. Vector A allows us to move up once, and we're going to use m vector a's. So 1 up, and vector b is down 3, and I'm going to have n of those, so down 3 n's. And we said to create vector x, the result had to be 3 up. So what we've managed to do is we've just created 2 equations. And those 2 equations have m's and n's in them. This is now a grade 10 problem. Right? We've got 2 equations and 2 variables. And the way we solved those was either using substitution or elimination. I am a big fan of elimination. So what I'm going to do, I think, is I'm going to try and get rid of the m's. And I'm looking at them going, well, the second equation has 1m, the first equation has 2. So I'm going to take equation 1, and I'm just going to leave it as it is. 2m plus n equals minus 8. And I'm going to multiply the second equation by 2. So that'll be a 2m minus 6n equals 6. So there's my equation. Now I should be able to eliminate them. There's a positive 2m and a positive 2m. So I should subtract these. The m's will cancel. I get a 7n equals minus 14. So n is equal to minus 2. So remember what that means. Go back to our statement up here. That's saying that to create vector x, I'm going to need negative 2 vector b's. Well, now that I've got that, I need to find m. So I think I'm going to sub that probably into this equation right here to find m. So m minus 3 times minus 2 equals 3. And what's that going to be? M plus 6. So m equals minus 3. if we solve that equation. So we need minus 3 vector A's and minus 2 vector B's, and then we'll end up getting our answer. That'll create what we wanted. So the way we would write that is we would say vector x is equal to minus 3 vector A's and minus 2 vector B's. And that's how we would create that. Now, that's a tough problem, and it's not obvious how you would do it, I don't think, by any means to start. But it's a good way of showing that it didn't matter what point I picked, we should be able to get this by using algebra. Remember, what we did was we said we were trying to get to the point minus 8, 3. So that made this x value here, right? We had to go left 8 and up 3. That corresponded to these two numbers in my system of equations. Well, if I change those numbers, I should still be able to use we used elimination. We should still be able to use elimination to solve for m and n. So it didn't matter what I picked, the minus 8 and the 3, I should have been able to come up with an answer no matter what. Now we were lucky here, I picked numbers that turned out okay with the minus 2 and the minus 3. You could have picked anything for vector x, and it would have been possible to come up with a solution. Probably would have had some decimals in it, but no matter what you pick, you can always come up with it. That's the idea of this linear combination. So if you take any two non-collinear vectors, you can combine them to create any other vector that you could possibly want. And that's going to be a really important idea for us, not so much in this unit, but a couple units down the road when we're going to start talking about lines and planes in three-dimensional space. The idea of having vectors representing other vectors can really make the difference. Okay, that wraps up this lesson. So a little bit trickier, I think, than some of our previous ones, but hopefully it went okay.